Okay, so thank you for the chance to present this work. First of all, I want to apologize in advance if I sound a bit distracted or exhausted. It's because today I got a second COVID shot and I start to feel a bit wear down, but we can manage through another 10 minutes, I hope. Um, okay, so here are the list of collaborators on this project, and I would like to highlight the roles of Santiago Gonzalez Gaitan and George Savic. So Santiago worked a great deal on data reduction analysis, while Georgia led the efforts on numerical simulations and modeling. Okay, you know this picture very well, so I just want to highlight that in this standard identification model, we usually have the dust is confined in the equatorial region in the form of so-called dusty torus. However, this has been challenged recently by several observations, namely in the single dish in the mid-infrared, we started seeing elongated mid-infrared emission on the scales of tens to hundreds of parsecs, but along the polar direction, so perpendicular to the accretion disk and the torus plane, so along the jet axis or along the ionization cone. So here you have a sample around 30 images, and the green line in all of them corresponds to this polar axis obtained by different measures, and the length of the line is a 100 parsec scale. Then similarly, it was found on the parsec scale by mid-infrared interferometry, namely the VLTI mid instrument. So probing the scales of only a few parsecs, and there again it was found that almost all the objects that were resolved and had extended emission, the extension was along this polar axis. So now the question is if this is simply a matter of projection and viewing angle, or if this polar dust is actually simply the galaxy ambient dust in the host galaxy limited by the accretion disk, or if it's, as it has been recently suggested, actually a dusty wind blown away from the innermost sublimation zone. So one of these sources is AGN in Circinus galaxy, so a very famous one, being among the nearest and brightest in infrared. It's basically archetype for obscured AGN. It has been observed across the whole wavelength range with high angular resolution. And here on the right, so you see the edges of the ionization cone. We see an optical. This broken line is showing the warped maser disk. And then this disk-like feature is the component seen by MIDI, coinciding with the maser. So it's probably a dusty disk, but it only has about 20% of the flux, while the majority of the flux come again from the polar region. And the orientation of this extension coincides with what we are seeing in the same source in the Viziers on larger scales. So a few years ago, we proposed a model to explain for this. So basically we have the thin layer of a dust shaped like a hollow cone enveloping the ionization cone, and then we have a tilted anisotropic accretion disk, which is producing this kind of emission. And okay, I don't have time to go into details, but in these two papers, we made numerical simulations, so ready to transfer images of these models, made simulated observations of how it would be seen if observed with Vizier and MIDI, and we have a quite good match in both morphology at all wavelengths, the spectra, the spectral energy distributions, and also this structure we see in with interferometry, so the correlated fluxes, so it all matches pretty well. So this is how we propose to be this as a prototype for this population of AGN with polar dust. On the left is the sketch, on the right is actually the ready transfer image of our model. So you see a thin disk slightly inclined and the hollow cone following the shape of hyperboloid. And then we launched a campaign to observe this with a number of other instruments on VLT, including NACO, Symphony, Muse, and of course Force 2, which I will talk about now. Okay, here are some technical details I will skip. I'll just say that we observed it in four filters, B, V, R, and I, and in the imaging polarimetry mode. This is the schematic of the reduction pipeline, the work done by Santiago Gonzalez. You can look it up in this paper. Apart from the usual stuff. I would highlight here that a lot of care was taken to account for the background sky and the instrumental field and interstellar polarization, and just flashing here the highlights. So basically it was found that there is the radial polarization pattern in the instrument field of view increasing up to 1.2%, but it was found that it can be characterized well by the paraboloid if you look at the polarization map, or by hyperpoloid if you look at the QNU map, so it can be accounted for. And then we could probe both the Milky Way and host galaxy interstellar polarization. And for this, we didn't have only a few stars as you do in spectropolarimetry, but the whole large field. So we can quite robustly account for both Milky Way and we think also of host galaxy polarization. And here are the resulting maps. So in the 4 filters, B looks a bit rough because we have only one offset. That'll look much better. And for example, here in the R, so here we have a nucleus, and here we see our ionization cone nicely. Okay, so for the modeling, we use the MCRT code skirt, which we also used previously for those models of thermal dust continuum I showed before. So it accounts for the anisotropic scattering and absorption on dust grains and electrons. And we explored again different geometries. Here I'm showing only the one, our favored model. So a small thin dusty disk and a hollow cone. We have maps on polarization angle, degree, Q and U, and intensity and polarized flux. And as a quick comparison, so here on the right, we have integrated polarization degree versus wavelength for these different geometries. So hyperboloid, paraboloid, and the classical dusty torus enveloped by host galaxy dust. From top to bottom, we have increasing viewing angle from face on to edge on. And here at the bottom, so in the red line, we have our favored model of disk plus wind. The black line is similar but shaped like paraboloid, and the blue one is corresponding to the torus model. And here on the left, we have the total polarization degree from observations in the green line, and you can see that the shape corresponds well to our model, while the torus one has a much bigger dip here. Okay, I should be wrapping up soon. I'll just say that we know that from other observations, there is significant extinction by the host galaxy disk. And to take this into account, to explore this, we also set up a couple of more MCRT models. So one is the analytical toy model consisting of a bulge and exponential disk filled with young and old stellar population and with dust in the disk. And the other is more realistic 3D model based on the Herschel 250 micron image, which we deprojected, then assigned a certain exponential electrical distribution profile. So we have now this full 3D model. And by running these simulations, we could also conclude that, for example, the smaller polarization degree, which is observed compared to the models, can be explained by this depolarization by the foreground dust. And we also see some other features in the host galaxy, which are again consistent with the simulations. And to conclude, so this polarimetric imaging data brought, so bringing 2 more observables, polarization degree and angle, really helps to put our model on the solid ground. So again, this is what we proposed as a prototype for this population of AGN with polar dust, now consisting of the disk and the hollow cone, now also supported by the polarimetric observations. Thank you.